Matt Roscoe at the University of Montana. Continuation of our lecture on section 3.2 from Burton's text on the Civ of Eratosthenes. So where are we at? We took a look at this already a bit in class, talked a little bit about the importance of Eratosthenes as a historical figure. Director of the Library of Alexandria, nicknamed Beta, a man of incredible scholarly reputation. We took a look at his algorithm for sieving primes, which involves sort of disallowing one, then identifying the first prime and disallowing any of its multiples, identifying the second prime, disallowing any of its multiples, third prime, fourth prime, and it turns out that after that we can construct an argument that we're done, and the numbers that remain on, I guess, the grid here must be prime. So part of your homework, you'll extend this grid to 200. Let's talk a little bit now about, well, how can we test numbers without constructing, let's say, a sieve for primality? So which numbers in the list below are prime? So I'm going to give you three different numbers, 231, 163, and 511, and talk about minimal trial divisions that have to be performed in each case. So let's go ahead and take a look at what that looks like. So 231, 163, and 511 are the three numbers in question. I've got them written down now. Let me get escaped out and take a look at these numbers. So there they are, 231, 163, and 511. So let's take the case of 231 first. So 231, is it prime is the question. Well, so one way we could do this is we could just simply divide by every possible number, less than 231, and see if it evenly divides 231, but that seems extremely inefficient. So one way we could think about it is, well, we could test, I guess, logically, divisors, potential divisors. So for example, the first one we might test is, does 2 divide 231? So what I'm going to do is make a little table. Let's call it n, and 231 divided by n, and talk a little bit about how many of these we have to test. So if I take 231 and divide it by 2, for example, what I find is that I get a decimal remainder. In other words, I get 115.5, so it indicates that 2 definitely doesn't divide it. So the next integer I could check is 3. If I divide by 3, I get 77, and 77 does divide it. So just in checking the first two trial divisions, I find out that 231 is indeed a composite number. So it is not prime. All right, well, let's switch over to 163. So if I have n and 163 divided by n, if I take 2, I can see right away that it's not going to divide it, but let's go ahead and just run through the game. 81.5. If I take 3, turns out 3 doesn't divide it either. I get 54.3 repeating. If I take 4, well, should I even check 4? The question there is, if 2 didn't divide it, could 4 ever divide it? And the answer is no, because 4 is a multiple of 2. So it turns out that I don't really have to check 4 if 2 fails. So let's move on to 5. Does 5 divide it? Well, no, I get 32.6 as an answer here. Does 6 divide it? Well, should I check 6? No, I shouldn't, because in order for 6 to divide it, 2 and 3 would have to divide it. So 6 can be skipped. And I guess the next number in question would be 7. Should I check 7? Yes, I should, because 7 is not a multiple of any of the numbers that have been checked before, and I get 23.2. let's call it dot, dot, dot. So 7 doesn't divide it. Should I check 8? Well, if 8 were to divide 163, then 2 would have to divide it as well, and since 2 doesn't, 8 can't. So we can disallow, or I guess skip checking 8. We can skip checking 9 because 3 doesn't divide it. 9 is 3 squared. We can skip checking 10 because 2 and 5 don't divide. We can skip checking 11, can we? No, we can't. So let's go ahead and try 11 and see what we get. When 11 divides it, we get 14.8 dot, dot, dot. So 11 doesn't divide it. Let's try 12. Does 12 divide it? Well, if 2 and 3 don't divide it, then 12 couldn't. How about 13? When I go to 13, I can see I get here as 12.5 dot, dot, dot. And I would argue that at this point we're done. The reason I would argue that is because you can see we've reached some sort of a turnaround spot in between 11 and 13, where the divisor and dividend now, prior to 11, the divisor was less than the dividend, and after 11, the divisor was greater than the dividend. So someplace in here we've reached a turnaround point. And of course, that turnaround point is the square root of the number. And in order for it to have, I guess, a divisor on this side, a dividend on this side that's actually a whole number, we could argue, well, we've already checked all the whole numbers that are less than that number, 11, 7, 5, 3, and 2, and all the ones in between by virtue of their compositely built of these numbers. So no number less than 12 is going to divide n because we've already checked everything up to 13. So I hope that makes sense. You know, what we've basically found is a test here for primality. And what it says is take the square root of the number, right? That tells you the turnaround point. So if I take 163 and hit the square root, I get something like 12.76, right? And the test would be to check every prime integer less than the square root, because that's in a sense what we did here is we checked every prime integer less than the square root of the number. And in fact, we went one beyond it, but we wouldn't have had to check 13 having known that the turnaround point was at 12.76. So all we'd have to do is test all primes less than the square root of 163. So that would just be 2, 3, 5, 7, and 11. And if it's not divisible by any of those 5, then we're done. And I hope that this is sort of impressed upon you that it's fairly efficient to check small numbers for primality if we know this algorithm. So let's apply it to something a little bit bigger, like 511. So I guess this was 1, 2, and 3. So 511 per, you know, I guess I didn't really say it, but I hope I made it clear that this one was composite, this one was prime. Okay, so let's try 511. So I'll make a table of values n, and 511 divided by n. If I plan out my attack, what I should probably do first is raise 511 to 0.5. So the square root of 511 is roughly 22.6. So we're going to check all primes less than 22. So that would be things like 2, 3, 5, 7. Let's see, 11, 13, 17, 19. And that would be it, right? So it looks like we'd have to do 1, 2, 3, 4, 5, 6, 7, 8 trial divisions. I'm going to do them fairly rapidly in my calculator. One way you can do this, of course, is to just put in the function 511 divided by x, and then go to the table to find out, well, what happens here when I divide by these prime numbers. So when I divide by 2, I'll write these out so you can see them. 255.5, so it's not divisible by 2, no surprise, it's not even. Divide by 3, I get 170.3. Divide by 5, no surprise there, 102.2, it's not divisible by 5. How about by 7? Well, 7 turns out to yield a divisor. It is 73. So 511 would indeed be composite because it can be divided by 7 and 70, or I guess it has two factors that are not 1 in itself. So it's a multiple of 7. What I want to make sure you understand is that there is a minimal strategy for checking for primality, and it involves starting with the smallest prime and checking all primes up to the square root of the number. Well, one big theorem about primes, now that we've kind of thought a little bit about their distribution and we've seen them in the sieve of Eratosthenes, one question you might have is there really an infinite number of these? And this is, regarded as one of the most elegant theorems in all of mathematics, the proof that there are indeed an infinite number of primes. So we better do this one and take a look at the logic behind the infinitude of the primes. Okay. All right. So I guess our hypothesis here is that there are an infinite number of primes. And what proof do we have of this? The proof I'm going to sketch, or I guess I'm going to reproduce, is Euclid's. And it appears in Book 9 of the Elements. And the method is the method of contradiction. So we proceed using a method of proof by contradiction. Okay, so what would it mean to prove it by contradictorily? If we're trying to show that there's an infinite number of primes, then what we would do is assume the opposite, right? We assume there are a finite number of primes, and here they are. If they're finite, they can be listed, right? So we could say something like, well, we know the first prime is 2 and the second prime is 3, but we could list these all up to some probably very large number, n, which is the last prime in the list. So some sort of infinite, or sorry, finite list of primes, p1 through pn. So if we have a finite list of primes, it's kind of interesting to think, well, how can we prove something, absurd? That's what we're looking for in a contradiction. We want to show that this results in some absurdity, some contradiction. And I think that the real genius in this proof is the next step, and that is this. Next, we construct the number. Here it is. I'll move this aside for a second. We're going to construct this number n, call it big N. We're going to let it be the product of all these primes, p1, p2, all the way up to p sub n, so this product of all the finite list of primes. But then what we're going to do is we're going to add 1 to that product. So to me, that's the real genius in the proof, is knowing the thought pattern that led to that choice, because this is where we're going to get our contradiction. So how are we going to get it? We're going to use the FTA. The fundamental theorem of arithmetic guarantees that n is divisible by some prime. Let's call that prime just P, regular old P. That is, P will divide N, right? I'm going to call this equation I, or 1. So this could take, the form of N itself could be prime, or N could be divisible by some other prime, right? So N is either prime or composite, and it's either divisible by itself, so P is a prime equal to N, or it's divisible by some other prime, okay? But here's where we're going to try to get a contradiction, and perhaps you see it already, but since P1, P2, up to and including Pn are the only primes available, what can we conclude? P must be equal to one of these. That is, P must be equal to some Pj where 1 is less than j, or equal to it, or equal to n. So j is one of these indices, 1 through n up here, and that prime has to be taken from this list of available primes. So far, so good. So what does that mean? So if P is one of these Pj's, right, then we can say that oops, sorry. So if it's one of those Pj's, what can we conclude? So if P is one of the Pj's, then P must divide this list P1 times P2 times all the way up to Pn. If it's one of the Pj's, it's got to be one of these, and it's got to divide that, right? And we're going to call this result 2. Now let's just kind of go back. What do we have? We've got result 1, P divides N. Result 2, P divides the list P1, or the product P1 times P2 times up to Pn. So if it divides both of these, it'll divide their sum or their difference or their product, and we have all kinds of divisive statements about divisibility that we can use at this point to combine these two things. And what I'm going to do is I'm going to combine them in as a linear product, and the linear product I want is the linear product n minus this product, because that will be equal to 1. So let me just go ahead and do that. So combining 1 and 2 as a linear product, a linear combination, sorry, we can conclude that P must divide n minus P1, P2, the product of P1, P2 up to P sub n, or just what? Well, we know that this guy, if I work a little magic on this one, well, n minus that product is just going to be 1. So, or just P divides 1. And now we have a contradiction. Why is this a contradiction? Well, because P itself is prime. By virtue of being prime, it has to be greater than 1, right? Because the first prime is 2. So we're in trouble, right? Which is exactly what we wanted. So let's just explain that, which is a contradiction as P is strictly greater than 1. So what can we conclude? Move this aside, make sure I'm in screen. So our assumption must be false. That is, there must be an infinite number of primes, which is what we set out to prove. And we're done. So often regarded as one of the most elegant proofs in all of mathematics. I hope I've done it a little bit of justice here. There are an infinitude of prime numbers. Okay, so just a couple other theorems and then we'll end this section. One interesting theorem is this, this idea of like, when can I predict another prime will come along? And it says if p sub n is the nth prime, then we always get an nth prime that's less than or equal to 2 raised to 2 raised to the power of n minus 1. So I want to show you that this really isn't all that informative. I mean, it is an upper bound on where the the nth prime occurs, but it turns out to be kind of a gross overestimate. Let's take a quick look in an Excel file. This is provided on the web page. Here in this row, I have the numbers, the natural numbers written. In this row, what I have is the prime associated with that natural number. So the first prime is 2, the second prime is 3, the 10th prime is 29, and so on. And here I have the expression 2 raised to 2 raised to the n minus 1. So what we're told by the theorem is that the nth prime, I guess this number 2, is less than or equal to 2 raised to 2 raised to the n minus 1, which in this case equality holds. And in this case 3 is definitely less than 2 raised to 2 raised to the first. So that's 2 squared or 4. In this case 5 is definitely less than 16. But you can see that rapidly the upper bound on where the nth prime is found, it grows wildly, right? Because we have a power function. So pretty non-informative as you move through, the larger primes. As I guess the prime's position grows, so does its upper bound. And at some point, only at the 11th prime, it's beyond the capacity of Excel to compute. So we can see that the theorem itself is kind of a gross overestimate, but it does provide a certain upper bound. The proof of this theorem is actually in your text, and you might take a look at it. But given its, utility, I think perhaps it's not as important as the next couple of theorems. So there's a corollary that says there are at least n plus 1 primes less than 2 raised to 2 to the n. I guess all that is an adjustment of the index. It tells us how many primes are less than a certain upper bound. So this again gives you a little bit of a density argument. So in other words, at the 4th position, there's at least 3 primes that are less than this number. Of course, those are the 3 primes right there. At the 5th position, there's at least 4 primes less than that number, and of course, those are the 4 primes right there. So that's what that theorem is about. This is just a corollary, an adjustment of the results of the previous theorem. So let's go on to more interesting is Bertrand's conjecture, who, his conjecture was that for the nth prime is always less than 2 raised to the n for n greater than or equal to 2. So we have to start with the second prime and move from there. So I guess what we're disallowing 2 to work for this particular theorem. So if we take a quick look here, we can see that for the nth prime, which is, if we start at 2, is 3, is always less than 2 to the n, which is 4. Okay, well that seems to work. 5 is less than 8. 7 is less than 16. 13 is less than 64. So what you can see is that this is, of course, a vast improvement as an upper bound over the previous theorem, because the upper bound is much closer to the prime itself. Although as we move down in the numbers, things often, just like in the previous case, the upper bound grows wildly because it is a power function. So again, this is Bertrand's conjecture. The proof is not provided in your text because it is a difficult proof, But allowing the proof leads to another interesting result. If Bertrand's conjecture is allowed, then it can be fairly quickly shown that the nth plus 1 prime is always less than 2 times the nth prime. So what does that mean? That means that this consecutive primes always occur in a bandwidth that's a multiple of 2. And to show you kind of how this works, take a look at what happens if I take, so 1.5 would be the p n plus 1 prime divided by p sub n. So that means that I take 3 and divide by 2, and the ratio there is 1.5. And this would be 5 divided by 3. So the ratio of consecutive primes, according to the theorem that we just, I guess, showed, should be always less than or equal. Is it strictly less than? I can't remember. Or equal to. No, strictly less than 2. So I've constructed the ratio of Pn plus 1 over Pn, and it should be strictly less than 2. And I think that's what we're seeing here. In fact, that seems to be the largest ratio, 1.66, and things seem to get smaller because some consecutive primes are quite close. But every now and then it jumps up again, and it's interesting to think about those ratios for small numbers. If I just say, take a look at this as a graph, let's go ahead and insert a scatter plot. Then you can kind of see that what's going on is, at least for small primes, that this ratio bounces around, but indeed is always less than 2, and seems to grow sort of randomly close to 1 as n gets large. So that is a showing, I guess, of what that theorem really says, but it does tell us that we're going to find another prime always in an interval double the width of I guess, the interval from 1 to the prime in question. So that's kind of an interesting statement too. And I believe that's all I wanted to do today for this particular chapter, 3-2. We'll move on and talk a little bit about 3-3 in the next video. And good luck on your homework on this section.